My name is Eric Lalos, and I'm the founder of Quantified Mechanics. We build data, analytics, and AI applications that deliver clear and significant value to manufacturing operations. I want to start with a simple idea. Most manufacturers don't struggle to manage and improve quality because they lack data. They struggle because the same failures keep coming back, driving cost, retests, and lost capacity. This is a practical look at how we've helped teams prevent failures at their test benches, improving yield and cost of quality without disrupting existing tests or workflows. Manufacturers already measure quality, efficiency, and productivity. You track first pass yield, failure rates, retests, and throughput. The problem isn't the lack of metrics. The problem is that these metrics tell you what happened, not what's driving them or why the same failures keep happening. The reason is because most tests are designed to answer one question: did the product pass or fail? They aren't designed to provide the context and data needed to analyze and understand root causes or prevent future failures. So leaders see the same pattern week after week. Failure rates are above target, first pass test yield and throughput are below target, while beneath the surface, the same hidden issues keep repeating. Everybody intuitively understands that there's significant opportunity to improve cost and margin by improving quality. Scrap, rework, and retests are what people complain about, but these are just the symptoms. Failures are the actual cost driver. Every failure slows the line, consumes operator time, pulls in engineering or quality, and displaces production. What makes this expensive is repetition. When a failure isn't understood, the same issues cause the same failures the same way again and again. That's how cost of quality becomes a structural problem instead of a temporary issue that's quickly identified and resolved. If you want to reduce failures, you need to understand them. Most systems capture the failure, very few capture the fix. When a unit fails, operators do real work to make it pass. That knowledge usually lives in tribal memory, and engineering and quality never really see it. When we capture fixes and use them effectively, several things happen. Repeat failures drop because operators get the right fix up front, and overall testing drops because engineers finally see what's happening on the floor and take corrective action. First pass test yield and throughput increases because quality sees what's causing failures. We also capture corrective action automatically, which matters for audits, compliance, and traceability, so you can connect this data to downstream issues like warranty. With our solution, failures and fixes are captured at the bench as the work happens. This data is reviewed and analyzed by quality and engineering to understand root causes. This provides the key data needed to eliminate future failures, improve first pass test yield, reduce cost of quality, and improve margin. Meanwhile, once the fixes are reviewed and approved, an AI integration automatically recommends them to operators as failures happen at the bench. This reduces repeat failures, wasted scrap, rework, and retest because operators are automatically getting the right fix first. And because all of this data is captured in real time, teams start to see the issues early. A bad batch of components, a test instrument drifting out of spec. Instead of discovering problems after dozens of failures, teams contain them quickly. We've seen real-time data eliminate hundreds and thousands of failures from an operation just through the mechanism of early detection. This works because it's a bolt-on, not a rebuild. Nothing about your test strategy changes. Nothing about pass or fail logic changes. Test engineers keep doing what they already do. Because the integration is non-intrusive, time to value is fast and risk is low. You see results while the line keeps running. The focus here is not on IT architecture, it's measurable improvement. Here's what this looks like in practice. I'm going to walk through a short demo showing how this works. The window on the left is an example of what one of your tests might look like in LabVIEW. I'm using this to replicate a test failure. The window on the right is our bolt-on application that captures that data and returns a recommended fix based on your test data and what's worked in the past. You can see that the error is well understood based on past data, and the recommendation is clear. Based on this, the operator updates their action and returns to test again. And this is the data that contributes to future fix information. They apply the fix, retest, and if it passes, that action saved with evidence. The next operator, shift, and failure doesn't start from scratch. This reduces trial and error and creates consistency across shifts in sites. Meanwhile, engineering and leaders are using the same data and taking action upstream. They can see which failure modes show up the most often, which fixes actually work, and how long each one takes. When a fix is repeatable, they can turn it into a standard work step, a test limit update, a calibration change, or a supplier or assembly correction. So operators get faster, more confident recoveries at the bench. Engineering gets a ranked list of the issues costing the most time and scrap, and that's the loop. Capture what worked, prove it with retest data, share it instantly, and then fix the root cause so the next unit doesn't fail the same way. The outcome is fewer retests, shorter time to resolution, higher first pass yield, a clear line of sight from test failures to real operational impact. When we talk about ROI, we show a range. On the low end, we assume we prevent only a small fraction of failures. We include it mainly to show the first year break-even point. On the high end, we assume repeat failures show up across benches and shifts. This is where the upside is. The pilot is how we measure where you land in this range using your own failure and retest data. This example uses conservative assumptions. If you run 1 million tests per year and see 100,000 failures, if the average failure costs about $50 in operator time, retest effort, and scrap, that's roughly $5 million a year tied to failures. We're not claiming to eliminate failures here. The goal is to reduce repeat failures in the areas causing the most pain. Even a modest reduction in repeats covers the cost quickly and then keeps pain back as the system continues to capture, reuse, and standardize what works. And this is where the loop becomes visible. Leaders get clear trends and before and after metrics. Engineers get that same data plus analysis that supports investigation and points to the actions that reduce repeat failures. Operators get practical guidance at the bench without changing their workflow or taking on extra training. Everyone's using the same data, one source of truth, so decisions move faster and you stop debating the numbers. To keep it practical, we prove it in a tight pilot first. One test area, a subset of benches or a bench, clear metrics that everyone agrees on. Most pilots run 2 to 3 months and land around 6 figures. The bar and the deliverables are simple. A working system and measured improvement. If the numbers don't move, it doesn't earn the right to scale. If repeat failures or retests are holding you back, this is meant to be tried safely, not sold aggressively. The next step is simply a short one-pager that shows how this works and where it tends to help. If that's useful, reply send and I'll share it. If it's not a fit, that's okay too. Thanks for taking the time to watch this presentation. If you have any feedback, comments, questions, or suggestions, please let me know.